Imagine stepping into a high-performance spacecraft, an engineering marvel designed to push the very boundaries of human exploration. You ignite the thrusters, and the ship accelerates, pinning you to your seat as you leave the Earth, the Moon, and eventually the solar system far behind. You keep the engines burning, continuously adding energy, constantly increasing your velocity. In our everyday experience, on highways and racetrons, applying a continuous force results in a continuous increase in speed. If a car has more horsepower and fuel, it goes faster. It seems entirely logical that with a sufficiently advanced engine and an endless supply of fuel, your spacecraft could accelerate indefinitely, eventually traversing the galaxy in mere days or even hours. Yet the universe harbors a profound, unbreakable rule, a fundamental law that shatters this intuitive assumption. No matter how much energy you expend, no matter how advanced your technology becomes, you will never reach, let alone surpass, the speed of light in a vacuum. This is not a limitation of our engineering, nor is it a temporary technological hurdle waiting for a genius inventor to overcome. It is an intrinsic, unyielding property of reality itself. To understand why the speed of light is the ultimate cosmic speed limit, we must embark on a journey that challenges our deepest common-sense notions about space, time, mass, and the very structure of the cosmos. For much of human history, light was considered instantaneous. From our terrestrial vantage point, when you strike a spark in the dark or watch lightning flash across a stormy sky, the illumination seems to arrive immediately, without any measurable delay. The ancient Greek philosophers debated the nature of light, with figures like Empedocles in the 5th century BC arguing that light was a substance moving through space, which inherently implied it must take some amount of time to travel. However, Aristotle later contended that light was simply the presence of something in a transparent medium, not a moving entity, and therefore its propagation was instantaneous. This view largely prevailed for centuries. In the early part of the scientific revolution, the brilliant astronomer Galileo Galilei attempted to measure the speed of light. Around 1638 AD, he proposed an experiment involving two people standing on distant hills, each holding a lantern with a shutter. One person would open their shutter, and the moment the second person saw the light, they would open theirs. By measuring the delay between opening the first shutter and seeing the return light, Galileo hoped to calculate the speed. Predictably, the experiment failed. The delay was simply human reaction time, as light traverses a few miles in a fraction of a millisecond. Galileo concluded that if light does take time to travel, its speed must be extraordinarily high, far beyond human ability to measure with simple lanterns. The first true breakthrough came not from Earth, but from observing the heavens. In 1676 AD, the Danish astronomer Ole Rømer was making precise observations of Io, the innermost of Jupiter's, for large moons. Rømer was timing the eclipses of Io as it passed behind Jupiter. He noticed a peculiar pattern. When Earth and Jupiter were relatively close to one another in their orbits around the Sun, the eclipses occurred slightly earlier than expected. Conversely, when Earth was farther away from Jupiter, on the opposite side of its orbit, the eclipses occurred slightly later. Rømer correctly deduced the reason for this discrepancy. The light carrying the visual information of the eclipse had to travel across the vast distance of space. When Earth was further away, the light had to cover a greater distance, taking more time to reach his telescope. Using these observations, Rømer made the first quantitative estimate of the speed of light. While his value was about 25% lower than the modern accepted figure, it was a monumental conceptual leap. Light was not instantaneous. It was a physical phenomenon with a finite, albeit staggering, velocity. Fast forward to the 19th century, a golden era for physics. The Scottish physicist James Clerk Maxwell was working on unifying the theories of electricity and magnetism. Through a series of elegant mathematical equations formulated in the 1860s, Maxwell demonstrated that changing electric fields generate magnetic fields, and changing magnetic fields generate electric fields. This continuous, self-sustaining oscillation creates an electromagnetic wave that propagates through space. When Maxwell calculated the speed at which these electromagnetic waves should travel, the result was astonishing. The theoretical speed exactly matched the best experimental measurements of the speed of light at the time. Maxwell realized that light itself was a form of electromagnetic radiation. This was a triumph of theoretical physics, But it introduced a deeply troubling question. If light is a wave, what is waving? Sound waves require air or water. Water waves require the ocean. Physicists reasoned that there must be an invisible, pervasive medium filling all of space that allowed light waves to propagate. They called this hypothetical substance the luminiferous ether. The existence of the ether became a central tenet of 19th century physics. Scientists believed that Earth must be plowing through this invisible ether as it orbited the Sun. If so, a beam of light shown in the direction of Earth's motion should travel at a slightly different speed relative to the Earth than a beam shown in a perpendicular direction, much like swimming upstream versus swimming across the current of a river. In 1887 AD, two American physicists, Albert A. Michelson and Edward W. Morley, devised an incredibly sensitive experiment to measure this ether wind. They used an interferometer, a device that splits a single beam of light into two perpendicular paths, bounces them off mirrors, and recombines them. If the speed of light differed along the two paths due to the ether wind, the recombined light waves would interfere with each other, creating a specific pattern. To their utter bewilderment, they found absolutely no difference. No matter which way they pointed their apparatus, no matter what time of year they conducted the experiment, the speed of light was always exactly the same. The ether did not seem to exist. More importantly, the Michelson-Morley experiment suggested a profoundly counterintuitive idea. The speed of light appeared to be constant for all observers, regardless of their own motion or the motion of the light source. Imagine a train moving at 100 miles per hour. If you stand on the train and throw a baseball forward at 50 miles per hour, someone standing on the ground watching the train go by would see the baseball traveling at 150 miles per hour. Velocities add up. This is Galilean relativity, and it matches our everyday experience perfectly. But the Michelson-Morley experiment implied that light does not obey this rule. If a spaceship is moving toward you at half the speed of light, and it turns on a headlight, you will measure the beam from that headlight approaching you at exactly the speed of light, not 1.5 times the speed of light. If the spaceship is moving away from you at half the speed of light and shines a light back at you, you still measure the light approaching at exactly the speed of light. This completely defied the established laws of physics and common sense. The resolution to this paradox came in 1905 AD from a young, relatively unknown patent clerk in Bern, Switzerland, named Albert Einstein. Einstein proposed a radical new framework, the special theory of relativity. He based his theory on two fundamental postulates. First, the laws of physics are the same for all observers in uniform motion, meaning anyone moving at a constant speed in a straight line. There is no absolute state of rest. Motion is entirely relative. Second, and most crucially, the speed of light in a vacuum is an absolute constant for all observers, regardless of their relative motion. Einstein simply accepted the bizarre result of the Michelson-Morley experiment as a fundamental truth of the universe and asked a profound question. If the speed of light is always the same for everyone, what else has to change? Velocity is simply distance divided by time. If the velocity of light remains absolutely fixed, then space and time themselves must be flexible, altering their fundamental nature to ensure the speed of light never varies. This realization led to conclusions that seem almost like science fiction. Einstein demonstrated that space and time are not absolute, rigid stages upon which the events of the universe play out. Instead, they are deeply intertwined into a single, flexible fabric known as space-time. When an object moves through space, it alters its progression through time. This phenomenon is called time dilation. From the perspective of a stationary observer, a moving clock ticks slower than a clock at rest. At everyday speeds, this effect is infinitesimally small, utterly imperceptible. But as an object approaches a significant fraction of the speed of light, the effect becomes profound. If you were to travel in a spaceship at 99% of the speed of light for 1 year, as measured by your onboard calendar, you would return to Earth to find that several years had passed for those you left behind. Your time actually slowed down relative to the rest of the universe. Equally bizarre is the phenomenon of length contraction. As an object accelerates, its physical length, measured in the direction of its motion, compresses from the perspective of a stationary observer. A spaceship traveling near the speed of light would appear squashed along its axis of travel. But to the astronauts inside, everything would appear perfectly normal, and they would instead see the universe outside compressing around them. Space and time warp and stretch, perfectly conspiring to ensure that no matter how fast you are moving, if you measure the speed of a passing photon, you will always get exactly 299,792,458 meters per second. But why is this constant speed specifically an unbreakable limit? Why can't we simply accelerate our spaceship past it? The answer lies in another consequence of Einstein's special relativity, perhaps the most famous equation in all of science, E equals mc squared. This equation states that energy and mass are interchangeable. They are different manifestations of the same underlying reality. When you accelerate an object, you are adding kinetic energy to it. According to E equals mc squared, adding energy is equivalent to adding mass. Therefore, as an object moves faster, its relativistic mass increases. Again, at low speeds, this increase is undetectable. But as an object gets closer to the speed of light, its relativistic mass begins to skyrocket. Imagine pushing a boulder. It takes effort to get it moving because of its mass. As you push our hypothetical spaceship faster and faster, its relativistic mass grows exponentially. As it approaches the speed of light, its mass approaches infinity. According to Newton's laws of motion, it takes a force to accelerate a mass. The more massive an object is, the more force is required to accelerate it. Because the spaceship's mass is becoming infinitely large, it requires an infinitely large force and an infinitely large amount of energy to accelerate it further. Since there is not an infinite amount of energy in the universe, it is physically impossible for any object with mass to ever reach the speed of light, let alone exceed it. The universe essentially pushes back, translating your applied energy not into more speed, but into more mass. This brings us to a fundamental distinction. The speed limit of the universe is not specifically about light. Light happens to travel at this speed because photons, the particles that make up light, are completely massless. Any particle that has absolutely zero rest mass must always travel at exactly this cosmic speed limit in a vacuum. If a particle has even a tiny fraction of mass, it must travel slower than this limit. Therefore, the speed of light is more accurately described as the speed of causality or the speed of information. It is the absolute maximum speed at which two parts of the universe can interact or communicate with each other. It dictates how fast a cause can produce an effect. Gravity also obeys this strict limit. Isaac Newton's original theory of gravity treated it as an instantaneous force. Newton believed that if the sun were to suddenly disappear, the Earth would immediately fly off into deep space in a straight line. But Einstein's general theory of relativity, which he published a decade after his special theory, refined this view. General relativity describes gravity not as a pulling force, but as the curvature of spacetime caused by mass and energy. The Earth orbits the Sun because it is following the curved spacetime created by the Sun's massive presence. If the Sun were to suddenly vanish, the sudden change in gravity would not be felt on Earth instantly. Instead, it would create ripples in the fabric of spacetime, known as gravitational waves. These waves travel outward at exactly the speed of causality, the speed of light. The Earth would continue to orbit an empty point in space for roughly 8 minutes, completely oblivious to the Sun's disappearance until the gravitational wave reached it. Only then would the Earth's path straighten out. Gravity, like electromagnetism, is bound by the universal speed limit. What would happen if we could somehow cheat the system and travel faster than light? According to the mathematics of relativity, breaking the light speed barrier would not just be an impressive engineering feat, it would profoundly break the logical structure of reality. Because space and time are interconnected, traveling faster than light is mathematically equivalent to traveling backward in time. This leads immediately to paradoxes that threaten the concept of causality itself. Imagine you have a faster-than-light communication device, a sort of hyperspace radio. You use it to send a message to a distant colony on another star system, asking them to immediately reply as soon as they receive it, because both the outgoing and return signals are traveling faster than light. Relativistic calculations show that the reply could arrive back to you before you even sent the initial message. You could receive a response to a question you haven't asked yet. This opens the door to the grandfather paradox. What if the message you receive is an instruction not to send the original message? If you obey the instruction and never send it, how did you receive the reply telling you not to? Cause and effect become tangled and contradictory. In a universe where faster-than-light travel is possible, causality breaks down. Events can happen before the things that cause them. To preserve the logical consistency of reality, where causes must always precede their effects, the speed of causality must be an absolute limit. Are there any exceptions to this rule? Sometimes things appear to travel faster than light, but these are illusions or misunderstandings of the physical laws. For example, consider the expansion of the universe. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther away they are, the faster they are receding. When astronomers observe the most distant galaxies at the edge of the observable universe, calculations reveal they are moving away from us at speeds significantly greater than the speed of light. This seems like a direct violation of Einstein's theories. However, the galaxies themselves are not moving through space faster than light. Instead, the space between the galaxies is expanding. Relativity dictates that no object can move through space faster than light, but it places no restrictions on how fast space itself can expand. The fabric of spacetime can stretch at any rate, carrying galaxies with it like dots drawn on an expanding balloon. Because the galaxies are not moving locally through their surrounding space faster than light, no laws of physics are broken, and no information is exchanged faster than causality allows. Another apparent exception is the phenomenon of quantum entanglement. In the bizarre world of quantum mechanics, two particles can become entangled such that their properties are intimately linked, regardless of the distance between them. If you measure the spin of one entangled particle and find it pointing up, you instantaneously know that the other particle's spin is pointing down, even if it is on the other side of the galaxy. This seems to imply that information is traveling between the particles instantaneously, infinitely faster than light. Einstein himself was deeply troubled by this, famously calling it spooky action at a distance. However, careful analysis reveals that quantum entanglement cannot be used to transmit usable information faster than light. The outcome of your measurement on the first particle is entirely random. You cannot force it to be spin up or spin down. Because you cannot control the outcome, you cannot encode a message into the entangled particles, while the correlation between the particles is instantaneous. Any attempt to use them to communicate requires sending a conventional slower-than-light signal to compare results. Thus, the speed of causality remains inviolate. There is also a fascinating visual effect called Cherenkov radiation, which occurs when particles travel faster than light. While nothing can travel faster than the speed of light in a perfect vacuum, light slows down when it passes through a medium like water or glass. In water, light travels at only about 75% of its vacuum speed. It is entirely possible for a highly energetic particle, such as an electron emitted from a nuclear reactor, to enter water traveling faster than the speed of light within that specific medium. When this happens, the particle creates a kind of electromagnetic sonic boom, emitting a distinctive, ethereal blue glow. But this is not a violation of relativity. The particle is exceeding the local speed of light in the water, but it is still traveling significantly slower than the absolute speed limit, the speed of light, in a vacuum. Some theoretical physicists have hypothesized the existence of bizarre particles called tachyons, which always travel faster than light. The mathematics of relativity technically allow for the existence of tachyons, but they would possess incredibly strange properties. They would have imaginary mass, and as they lost energy, they would accelerate, reaching infinite speed when they had zero energy. To slow a tachyon down to the speed of light would require infinite energy. However, there is zero experimental evidence that tachyons exist, and most physicists consider them a mathematical curiosity rather than a reality, precisely because their existence would lead to the very time travel paradoxes and causality, violations that the universe seems strictly structured to prevent. The speed of light, approximately 300,000 kilometers per second, is not an arbitrary number. It is a fundamental property of the vacuum, deeply woven into the constants of nature. It relates to the electrical permittivity and magnetic permeability of empty space. The resistance of the vacuum to the formation of electric and magnetic fields, in a very real sense, the speed of light is a measure of the stiffness of spacetime itself. It is the maximum rate at which reality can update. We often view limits as obstacles to be overcome. The speed of light barrier can feel incredibly frustrating when we dream of exploring the stars. The nearest star system to Earth, Alpha Centauri, is over 4 light-years away. This means that even if we could travel at 99% of the speed of light, it would take years to get there. The Milky Way galaxy is roughly 100,000 light-years across. For all intents and purposes, the vast majority of the universe is permanently quarantined from us by this fundamental law. It can make the cosmos feel isolating, immense, and ultimately inaccessible. But there is another way to look at it. The universal speed limit is the glue that holds the universe together in a logical, coherent manner. Without it, cause and effect would lose all meaning. The past, present, and future would jumble together into a chaotic, nonsensical mess. Energy would not be conserved in the way we understand it, and the complex structures of the universe, from atoms to galaxies, could not exist. The unbreakable nature of the speed of light is precisely what allows the universe to be predictable, to have a history, and to support the existence of observers like us. It forces us to confront the profound interconnectedness of space, time, and mass. It tells us that we are not living on a fixed, rigid stage, but within a dynamic, responsive, and incredibly elegant framework. The speed limit of reality is not a prison. It is the very architecture of existence. By understanding and respecting this boundary, we gain our deepest insights into the true nature of the cosmos.